On July 14, 2005, a spacecraft named Cassini flew past a tiny frozen moon that every textbook said should be dead. Enceladus is barely 300 miles across. You could drive across it in a day. It orbits Saturn, almost 1 billion miles from the Sun, in a place so cold that water ice behaves like solid rock. There's no reason a rock that small should be doing anything at all. Then Cassini turned its instruments toward the South Pole, and the data came back wrong. Something was pouring out of that moon. Not slowly, not gently. Hundreds of miles of water vapor, blasting into space at 800 miles per hour. This is the story of the strangest moons we have ever found, and why the search for alien life just moved into some very unexpected places. If you enjoy this kind of deep dive, hit subscribe. This channel goes into the science of habitable worlds every single week, and there is a lot more coming. For most of the history of astronomy, the rules for where life could exist were simple, and they were built around one idea: the habitable zone. It works like this. You take a star, you calculate how much heat it puts out, and you draw a ring around it. Too close to the star and any water on a planet's surface boils away. Too far and it freezes solid. The ring in between, where liquid water can sit stably on a surface, is the habitable zone. Sometimes scientists call it the Goldilocks zone because it is not too hot and not too cold. It is just right. In our solar system, that ring is narrow. Venus sits just inside the inner edge, a furnace with surface temperatures around 870 degrees Fahrenheit and clouds of sulfuric acid. Mars sits near the outer edge, a frozen desert that lost its atmosphere billions of years ago. Earth sits in the middle, comfortable, wet, and alive. Everything beyond Mars was considered a write-off. Jupiter, Saturn, Uranus, Neptune, and the hundreds of moons circling them were filed under one word: frozen, dead, case closed. That model was clean, it was elegant, and it turned out to be enormously incomplete, because the habitable zone only accounts for one source of energy: sunlight. And sunlight is not the only way to keep water liquid in a cold universe. To understand what broke the model, you need to understand tidal heating. The easiest way to feel it is with your own hands. Take a paperclip and bend it back and forth, over and over, as fast as you can. After 20 or 30 bends, touch the metal where you were flexing it. It is hot. You did not apply any heat. You did not light a match. All you did was force the material to flex, and the friction of that flexing generated heat from nothing but motion. Now scale that up to the size of a moon. When a moon orbits a giant planet on a slightly stretched, non-circular path, the planet's gravity pulls harder on the near side than the far side. As the moon swings closer, it gets squeezed. As it swings away, it relaxes. Every single orbit, the entire body of that moon flexes like the paperclip. The rock strains, the interior grinds against itself, and that friction generates heat. Enormous amounts of heat, continuously for billions of years, with no sunlight required at all. That is the loophole. Life needs liquid water and an energy source. The habitable zone assumes both come from a star. Tidal heating says otherwise. And it means the outer solar system, the part we wrote off as a frozen graveyard, might be the most water-rich real estate we have. Let's start with the moon that proved tidal heating was real, because it did not do it politely. In March of 1979, Voyager 1 was flying through the Jupiter system, and a young NASA navigation engineer named Linda Morabito was doing something completely routine. Her job was optical navigation. She would take images the spacecraft had captured, find known stars in the background, and use their positions to pin down exactly where the spacecraft was in space. It is careful, unglamorous, essential work. She pulled up an image of Io, one of Jupiter's 4 large moons, and deliberately overexposed it so the faint background stars would show up against the darkness. And there, on the edge of Io's disk, was something that should not have been there: a huge, umbrella-shaped cloud rising more than 160 miles above the moon's surface. Her first thought was that it was a camera artifact, a smudge on the optics. Her second thought was that it might be another moon peeking out from behind Io. She checked the ephemeris data. There was no moon there. There was nothing there at all except Io and empty space. She had just discovered the first active volcano ever found beyond Earth. That umbrella was a volcanic plume, and it was so violent that it was throwing material clear off the moon and into orbit around Jupiter. What makes this better is the timing. 3 days before Voyager sent those images home, a paper had been published in the journal Science by Stan Peele, Patrick Casson, and Ray Reynolds, predicting that Io should be volcanically active because of tidal heating from Jupiter. They ran the math and concluded the moon's interior should be melting. The paper hit print, and almost immediately, a navigation engineer looking for background stars found the proof sitting in the image. Io is now the most volcanically active body in the solar system, with more than 400 active volcanoes. Its surface is repaved constantly with sulfur compounds, which is why it looks like a rotting pizza in every photo you have ever seen of it. Some eruptions launch material 250 miles into space. The moon is squeezed so hard by Jupiter's gravity that its solid surface rises and falls by up to 300 feet. Not the ocean. There is no ocean. The ground itself heaves 300 feet, twice per orbit, forever. Io is a nightmare. Nothing lives there. But Io proved the mechanism. Tidal heating was not a theory anymore. It was a fact you could photograph. And that raised an obvious question. If Jupiter can melt the inside of Io, what is it doing to the moon right next door? Europa is roughly the size of our own moon, and from a distance it looks like the most boring object in the solar system. It is smooth, almost perfectly smooth, one of the smoothest solid surfaces we know of anywhere. There are almost no craters, which is deeply strange because everything in the solar system has been hammered by impacts for 4.5 billion years. A surface with no craters is not an old surface. It is a young one. Something is erasing them. But look closer, and the smoothness is covered in cracks. Long, dark, reddish-brown lines that stretch for thousands of miles, curving and crossing each other in patterns that look almost exactly like the fracture patterns in sea ice on Earth's Arctic Ocean. That resemblance is not a coincidence. Beneath Europa's ice shell, somewhere between 10 and 15 miles thick, there is an ocean of liquid salt water. We are extremely confident about this, and the strongest evidence came from magnetism. When the Galileo spacecraft flew past in the late 1990s, it found that the moon generates its own magnetic field, but a strange one. It flips direction as Europa moves through Jupiter's magnetic field. That signature is what you get from a conducting layer inside the moon, and the most plausible conductor is a global ocean of salty water. Here is the part that stops people cold. That ocean is estimated to be somewhere between 40 and 100 miles deep. Earth's oceans average about 2.3 miles deep, and the deepest point we have, the Challenger Deep, is under 7 miles, which means Europa, a moon smaller than Earth, contains roughly twice as much liquid water as every ocean, sea, lake, and river on our entire planet, combined. Twice as much water as Earth, on a moon, 500 million miles from the sun. And that ocean is not sitting in a sterile bathtub. It is almost certainly touching a rocky seafloor, warmed by the same tidal flexing that tears Io apart. On Earth, where hot rock meets seawater, you get hydrothermal vents. And around those vents, you find some of the densest ecosystems on this planet. Communities of tube worms and crabs and microbes that have never seen sunlight and do not care. They run on chemistry, not photosynthesis. We did not even know those ecosystems existed until 1977. Before that, biology textbooks stated that all life on Earth ultimately depends on the sun. That statement was wrong, and we found out only 48 years ago. Europa may have been running that same experiment in the dark for 4 billion years, which brings us back to the small moon from the beginning of this story, because Enceladus went one step further. It did not make us guess what was in its ocean. It sprayed it directly into our spacecraft. When Cassini detected that plume in 2005, the mission team faced an uncomfortable decision. They could log the discovery, take the pictures, and continue with the mission they had planned for 2 decades. Or they could rewrite the flight plan and fly a billion-dollar spacecraft directly through a jet of material erupting off an alien moon at high speed. No one knew what was in the plume. If it contained ice grains large enough or dense enough, they could damage the instruments. Cassini was not built for this. Nothing was built for this, because before that year, no one thought a moon that small could erupt at all. They did it anyway. Over the following years, Cassini flew through the plumes repeatedly, each pass lower and more aggressive than the last. In October of 2015, it dropped to just 30 miles above the surface and punched straight through the densest part of the spray at 19,000 miles per hour, tasting the ocean of another world without ever landing on it. What it found rearranged the field. The plume contains water, obviously, but it also contains salt, in roughly the proportions you would expect from an ocean in contact with rock. It contains silica nanograins, particles that on Earth form only when water hotter than about 190 degrees Fahrenheit interacts with rock. That is direct evidence of hydrothermal activity on the seafloor of a moon 800 million miles away. It contains methane in quantities difficult to explain through geology alone. On Earth, most methane is produced by living organisms. It contains molecular hydrogen, which is the single most useful thing on this list, because hydrogen plus carbon dioxide is a chemical meal. It is exactly what certain microbes on Earth eat at deep sea vents. Cassini did not just find water on Enceladus, it found a food source. And then, in 2023, researchers went back through the Cassini data with better analysis techniques and found phosphates. Phosphorus is the rarest of the 6 elements essential to life as we know it. It is in your DNA. It is in your cell membranes. It is in the molecule your body uses to move energy around. Finding it dissolved in the ocean of Enceladus, at concentrations apparently higher than in Earth's own seawater, removed the last major question mark on the ingredient list. Enceladus has liquid water. It has heat, it has organic carbon, it has nitrogen, it has hydrogen, it has phosphorus. It has a rocky seafloor with hot water flowing through it. There is not a single known requirement for life that Enceladus lacks. We have not found life there. That needs to be said clearly. Having every ingredient in the kitchen is not the same as having a meal on the table. But a decade ago, whether the outer solar system could be habitable was speculative. It is not speculative anymore. The habitability case is closed, only the occupancy question remains. Now let's talk about the moon, that decided to be weird in a completely different direction. Titan is Saturn's largest moon, and it is bigger than the planet Mercury. It is the only moon in the solar system with a thick atmosphere. And thick is an understatement. The surface pressure is about 1.5 times sea level on Earth. If you stood on Titan without a pressure suit, the pressure would not be your problem at all. You would need oxygen and you would need a very serious coat, because the surface temperature is around minus 290 degrees Fahrenheit. At that temperature, water ice is hard as granite. It is bedrock. It is the rock that Titan's mountains are made of. But methane, which on Earth is a gas you burn in a stove, is a liquid at Titan temperatures. And that changes everything, because Titan has a full weather cycle, not a water cycle, a methane cycle. Methane evaporates from Titan's surface. It rises, it forms clouds, it rains back down in fat, slow drops that fall 6 times slower than raindrops on Earth because of the low gravity and thick air. That rain carves river channels into the ice bedrock. Those rivers flow downhill, they braid and meander exactly the way rivers do on Earth, and they drain into lakes and seas. Titan's largest sea, Kraken Mare, is bigger than the Caspian Sea and more than 1,000 feet deep in places. There are shorelines, there are estuaries, there are islands, there are what appear to be waves, and around the equator there are dunes. Enormous fields of dunes hundreds of feet tall, stretching for thousands of miles, sculpted by wind into the same shapes you see in the Sahara. Except the sand is not sand. It is grains of solid organic material, complex hydrocarbons that formed in the upper atmosphere when sunlight broke apart methane molecules and then drifted down and piled up over millions of years. Titan is a world with rain, rivers, lakes, seas, beaches, dunes, and seasons. It is the most Earth-like surface in the entire solar system, and it is built entirely from the wrong materials. On January 14, 2005, the Huygens probe separated from Cassini and parachuted down through Titan's haze. It was the most distant landing humanity has ever attempted. No one knew what it would land on. There was a serious chance it would splash into a liquid sea, and the engineers had actually designed it to float, just in case. It touched down on a damp plain scattered with rounded pebbles of water ice, tumbled smooth by flowing liquid, and it sent back the only photograph ever taken from the surface of a world in the outer solar system. It kept transmitting for 72 minutes after landing. And here's the thing about Titan that keeps astrobiologists up at night. It also has a subsurface water ocean, under the ice, like Europa and Enceladus. So Titan gives you 2 independent shots at life. There is the conventional water ocean underneath, and then there is the surface, where an entirely different kind of chemistry has been running in liquid methane for 4 billion years. If anything is alive in those methane lakes, it would not be a variation on us. It would be a completely separate invention, and we would have no idea what to look for because every biology textbook ever written assumes water. There are more of these, and they get stranger. Triton orbits Neptune backwards. Every other large moon orbits in the same direction its planet spins, because they formed alongside the planet from the same disk of material. Triton goes the wrong way, which means it did not form there. It was captured. Triton is almost certainly a dwarf planet from the Kuiper Belt, a sibling of Pluto, that wandered too close to Neptune and got caught. And when Voyager 2 flew past in 1989, it found geysers of nitrogen erupting 5 miles into the sky, on a world where the surface temperature is minus 391 degrees Fahrenheit, the coldest measured surface anywhere in the solar system. Triton is probably hiding in Ocean 2. Its backwards orbit is slowly decaying, and in a few billion years, Neptune's gravity will tear it apart and give the planet a ring system brighter than Saturn's. Miranda, a small moon of Uranus, looks like it was smashed to pieces and reassembled by someone who was not paying attention. It has a cliff called Verona Rupes that is around 12 miles tall, more than 10 times the depth of the Grand Canyon. If you walked off the edge, the gravity is so weak that you would fall for about 12 minutes before hitting the bottom. Iapetus, another Saturn moon, is two completely different colors. One hemisphere is as bright as snow, the other is darker than coal. And running along its equator is a mountain ridge more than 800 miles long and up to 12 miles high, which makes the moon look like a walnut. No one is certain how it got there. And Mimas, the small Saturn moon with the enormous crater that makes it look uncomfortably like the Death Star, was assumed for decades to be a frozen lump straight through. In 2024, a team analyzing tiny wobbles in its rotation concluded that Mimas almost certainly has a liquid ocean under its ice too. And the ocean appears to be young, possibly only 5 to 15 million years old. If that holds up, ocean worlds are not just common. They can switch on. A moon that was dead can become habitable, on a timescale shorter than the age of the human genus. So step back and count. Europa, Enceladus, Titan, Ganymede, which has an ocean of its own and is the largest moon in the solar system, Callisto, Triton, probably Mimas, possibly Dione, possibly Pluto, which is not even a moon. That is potentially 9 or more bodies with liquid water oceans in a single solar system, and only one of them, ours, is in the habitable zone. The math on that is brutal in the best possible way. If liquid water on a surface requires a narrow orbital ring around a star, then habitable worlds are rare. But if liquid water mostly lives underground, kept warm by tidal flexing and radioactive decay, then the habitable zone is almost irrelevant. Icy moons vastly outnumber rocky planets in the right orbits, and an ocean sealed under 10 miles of ice does not need a magnetic field, does not need an atmosphere, does not care about stellar flares, and does not get sterilized by radiation. In terms of long-term stability, a buried ocean may be a far better place to keep life alive than a planetary surface. Earth might not be the standard model for a living world, Earth might be the exception, and Europa might be the rule. This is not a thought experiment anymore. In October of 2024, NASA launched Europa Clipper, a spacecraft the size of a basketball court carrying the largest solar arrays NASA has ever flown. It arrives at Jupiter in April of 2030 and will make roughly 49 close passes over Europa, mapping the ice, measuring the ocean's depth and saltiness, and sampling any material venting from the surface. It is not a life detection mission. NASA is explicit about that. It is a habitability mission, there to determine whether the conditions are right. And in April of 2023, the European Space Agency launched JUICE, which arrives around 2031, and will eventually settle into orbit around Ganymede, becoming the first spacecraft in history to orbit a moon of another planet. Then there is Dragonfly. NASA is sending a nuclear-powered rotorcraft to Titan, a drone, essentially, but one the size of a small car with 8 rotors. It will not roll along the ground like a Mars rover. Titan's atmosphere is thick, and its gravity is weak, which makes it the easiest place in the solar system to fly. Dragonfly will lift off, cruise for miles, land somewhere new, and study the chemistry there. Then do it again. Over its mission, it will visit dozens of separate sites, hunting for the signatures of prebiotic chemistry, the steps that come before life. It launches in 2028 and arrives in the 2030s. Within about a decade, we will have a spacecraft mapping Europa's ocean, a spacecraft orbiting Ganymede, and a drone flying through the sky of Titan. Here is why this matters more than almost anything else we are doing in science. If we find life on Enceladus or Europa, it will not be intelligent. It will be microbial. There will be no signal, no ruins, no ships. And it will still be the most important discovery in human history, for one reason that has nothing to do with the organism itself. Right now, we have exactly one example of life. Every living thing on Earth, every bacterium, every redwood, every whale, every person is built from the same genetic code and descends from the same ancestor. One data point, and with one data point, you cannot tell whether life is a routine chemical outcome that happens wherever conditions allow, or a freak accident that happened once and never repeated. Find a second independent origin of life on a moon in our own solar system, orbiting the same star, and that ambiguity evaporates instantly. If life started twice in one solar system, it started everywhere. The universe would go from possibly empty to certainly crowded in a single measurement. And we would learn it in our own backyard, from a moon we spent centuries dismissing as a rock. For most of human history, we looked at the night sky and assumed the interesting things were the bright ones, the stars, the planets. The moons were background, debris, rounding errors in someone else's orbit. We were looking at them completely wrong. The bright, warm, sunlit worlds turned out to be mostly dead, and the small frozen ones we ignored have been quietly holding oceans the whole time, dark and salty and warm at the bottom, churning through the same chemistry that built us for 4 billion years while nobody was watching. The next few decades are going to be extraordinary. If you got something out of this, hitting the like button genuinely helps this channel reach people who would find it interesting. And subscribe if you want to be here for the next one, because we are going to look at what happens when a star dies and leaves behind something that should not be able to exist. An object so dense that a single teaspoon of it weighs as much as a mountain, spinning 700 times per second and pointing a beam of radiation at the Earth like a lighthouse we accidentally learned to read.